on the air.
Okay, good morning, everyone over there in the US. It's very late in the evening here, soon to be very early in the morning. I'm Mark Jessop. Outside of hobby, I'm an RF engineer, and as a hobby, amateur radio and balloons. So this talk, hang on, let's get the right mouse in the right spot. There we go. This talk is a bit of a grab bag of topics to kind of explain what's been going on down here in Australia and the various tools we've been developing over the last 10 years or so that or at least that I've been involved. So go through what my local ballooning group's doing, Radiosonde Tracking, SondeHub, the Horus binary modulation, which we're using now, and then into SondeHub-Amateur, Chase Mapper, and also our imagery downlink system as well, which I figured I'd touch on. So our local group is Project Horus. Bill may remember Terry Baum. We started in 2010, and we've done about 60 launches or so far. We've done numerous payloads for numerous groups. Our claim to fame is we did some reference video for the movie Gravity, which was kind of fun. And we're on the special features on the DVD, which is kind of cool. And we've done various flights. Our common thing nowadays is live imagery, so live photograph downlinks through the Wenet system. We've also done live video as well a few times. We never used APRS. We followed the UK approach, so initially running RTTY on 434 megahertz, and then we've now switched to using the Horus binary mode and RS41s for primary tracking. Everything we develop is open source, and you'll see a lot of GitHub links throughout this presentation. So jumping across to radiosondes. So I think most people here know what a radiosonde is, you know, a sensor for doing meteorological research and producing data for weather models. Generally, it's a PCB with a radio transmitter, some sensors, and a microcontroller. Various common sensors, temperature, humidity, pressure, sometimes ozone, and of course, wind speed and direction, usually via GPS nowadays. Radio signals vary depending upon where you are in the world, but most commonly between 400 and 406 megahertz. There are still some holdouts running on 1.68 gigahertz, though not many left. Launch sites, there are many of them. Every little circle on that map is a World Meteorological Organization and registered launch site. I don't know what the number is. I should have written that down somewhere, but I didn't. And here's the launch sites in the US, and there are lots of them. There will be one near you, I can guarantee it. So what is launching in the US? And this is specific to the US. Probably, I must admit, the 30% here is worldwide. It's actually less than that in the US, but the Vaisala RS41 is the most popular radiosonde worldwide. 30% of worldwide launches. So it runs 4800 baud FSK, a bit of forward error correction, and it's commonly found in 400 to 406 megahertz, usually on 100 kilohertz boundaries. Inside of it, there's a microcontroller, a GPS unit, and a radio transmitter, and some Vaisala special source in terms of the temperature and humidity stalk. There's also 2 free AA lithium batteries, slightly used, and there is open source replacement firmware for this, which we'll get into a little bit later on, though Mike will cover that more. In the US, it appears the most common 400 megahertz sonde nowadays is the Graw DFM17, which is this radiosonde here on the right, and I've got one in my hand as well. These only came out a few years ago, and they run a lower data rate, 2500 baud, same frequency band, very similar internals in terms of microcontroller. They use a more modern GPS, so a U-Blox 8, which is a really nice, and a more modern radio transmitter IC, so a bit more capable. Unfortunately, there hasn't been much work done on reverse engineering these yet, and they use different batteries. They use CR123s, but there's some very good potential here for reflashing these and reusing them. Finally, I'm going to say last but not least, but least I think is a good term here at this point, is the LMS6. Really, I've only ever seen these in the US. These have been phased out in many locations, and this is quite an old design of radiosonde. They are the biggest one that's flying nowadays that isn't an ozone sonde. But yeah, these are generally being replaced by DFMs and the RS41 radiosondes. There are still a couple of holdouts, I believe, launching on the 1680 megahertz, but they'll be gone soon. So how do we go and receive all of these Radiosonde telemetry? So I developed a bit of software called Radiosonde Auto-RX. This was built out of the need to try and find the frequency that was in use by my local launch station on any given day. They used to change frequencies almost daily for whatever reason, made it very hard to find out what was going on. So I wrote a bit of software which would scan the Radiosonde band, do some peak detection, find out if that particular peak was a Radiosonde, what type was it, and start decoding. This then expanded to support a lot more Radiosonde types, to the point that now we support pretty much every common Radiosonde type that's used worldwide. It was targeted basically at a Raspberry Pi style platform. They would run on a lot of different platforms nowadays. There's currently 600 stations running this software, and we're using software-defined radio, and there's a GitHub link there. So what's it doing internally? So we're using software-defined radio to basically to capture the Radiosonde band. We do some spectral analysis to try and find these peaks in this band, which might be a signal that we're interested in. For each of these peaks, we run it through what we call a sonde detector. This uses the known headers of the various Radiosonde types, and they're all different enough that we can determine which signal is which Radiosonde very, very reliably. Once we've found a Radiosonde, we start decoding and uploading telemetry to various places, such as the SondeHub tracker, which I'll get into in a second, and also ChaseMapper, which I'll get into later on. You'll note that APRS is not on this list. APRS.fi, as of about 3 months ago, started blocking Radiosonde traffic from their map. Not amateur balloon traffic, but Radiosonde traffic, because there was far too much of it. During the points when Radiosondes are launched, for quite some time, about probably 40% of all of APRS IS was Radiosonde traffic, which is not a good thing. So that's been culled back quite significantly in recent months. So Auto-RX, once you run it, has a web interface. Here's an example of it, where we can see our spectrum scan, the number of peaks, which are mostly local noise, but there is one there which actually is a Radiosonde signal. Up the top, we can see the telemetry being decoded from that Radiosonde signal, and a map showing where it is with respect to your station. This is all local. This is just your local receiver status. But what's more important is, actually, sorry, one last thing I should mention here. As of about 2 weeks ago, the support's been added to use an AirSpy and Spy server. And yes, Phil, I'll be adding support for your software as well soon, to monitor the entire Radiosonde band in one hit and decode everything that it can see. So here's an example showing 5 Radiosondes being decoded simultaneously from over in Europe. So this is very new, very, very untested, but this is quite exciting. So Radiosonde Auto-RX needs to upload telemetry somewhere. So when the project started, we started uploading telemetry to HabHub. Many of you may be aware of HabHub. The UK started amateur radio balloon tracking website. At this point, there was only a handful of stations uploading. It wasn't really a big deal. In 2018, I think by that point we had about 30 or 40 stations. We purchased the SondeHub domain. We used it as a redirect to HabHub, just with some filtering to only show Radiosondes. About this time, HabHub modified their site to filter out the Radiosondes, which was probably a good idea given they were populating the map and filling it up quite a lot. About a year later, things got pretty bad. There's about 99% of traffic on HabHub was Radiosondes. That caused some database problems and some slowdowns. We were very apologetic about that. And we switched across to using our own database and backend system, which we run in Amazon Web Services. In late 2020, we forked the HabHub tracker. Actually, early 2020? I think it was early 2020. We forked the HabHub tracker and we started adding Radiosonde specific features, and we pointed it at our own database. This allowed us to do all sorts of interesting things. And another note there is that in early 2022, APRS.5 started blocking Radiosonde traffic. So APRS.5 could no longer be used to look at Radiosondes. So today, the database is, everything's publicly available. We use the CC BY SA Creative Commons license for all of our data. We have APIs, we have live data streams, everything's available to anyone who wants to look at it and use it. The database is not just limited to Radiosonde Auto-RX. There is other software that can use it as well. So the RDZ TT-Go sonde is some firmware for some small LoRa receiving devices, which can also receive straight FSK. They're quite popular. And also SondeMonitor. Many of you may be aware of SondeMonitor. It does support uploading to SondeHub, at least for RS41s. Bev is probably going to add support for the other Radiosondes over time. At the moment, we're seeing something in the vicinity of 300 to 400 unique Radiosondes per day, of which we capture quite a lot of the traffic. There are currently, as of today, 750 receiving stations in total contributing data, and we see about 7 million Radiosonde telemetry packets per day. Information on the API is available at that link. And also, very important to note, we are sponsored by Amateur Radio Digital Communications. They pay our AWS bill, which is amazing, because otherwise we probably wouldn't be running this anymore. It'd be getting very expensive. So SondeHub, I'm going to give a brief demo, because why not? And can I just check you're still seeing my screen?
Yes, we are.
Beautiful. So this is SondeHub. It looks very similar to HubHub, if you're familiar with that. This is the US, of course, and these are all Radiosondes. And we've actually just had the 12 Zulu Radiosonde launch. Sondes launch generally twice a day, around about 0 and 12 Zulu, though some sites launch at other times as well. And so each of these, it was a Radiosonde launch. Each of the green or orange dots is a receiving site. Each of these other dots is a launch site. And based upon information we can glean from the WMO database, you can click on a launch site. You can find out some information about it. So I'm going to do an example here of North Platte, where we can see the Radiosonde type that's launched, the frequency, which it's commonly seen on, and when it launches. So if you go to this site and find a launch site near you, you can click on that and you can get an understanding of what's being launched in your area. Another useful feature, and I'm going to go up to Mike's area just for fun on this one, and go look at the Buffalo launch site, is the Generate Predictions button. Now, because we know what the launch schedule is and we have access to weather models, we can predict where these balloons are going to go. So there we go. There is all roughly the next week's worth of launches for Buffalo. So the next launch at 11, well, this is my local time, so 6 Zulu, or no, sorry, whatever time that is in UTC, sorry. And then the next launch after that, and after that, and after that, and so on and so forth. What else have we got? So we can also upload our position to the map as a chase car if we choose to when we're out and about hunting, by ticking this button here and allowing location services. Normally you'd run this on your mobile phone. And when you recover a Radiosonde, you can also report the recovery using this page as well. As an example, down here near Phoenix, someone's been very busy, and we can see these recent recoveries by KE7HR on a parking shade still transmitting. So you can get a good picture of what's happening near you. Most likely there'll be a station receiving a Radiosonde near your area, so you can see what's being launched and work out what to look at. So that's SondeHub. So jumping tack a bit. Let me just grab a drink. So this is something which we've been working on for a while now, probably about 4 or 5 years. So as I said earlier on, we never used APRS in our flights. There wasn't much of an APRS network available, and it really wasn't reliable down to the ground. And we started off using using RTTY, which has no forward error correction at all, which is pretty terrible. So a couple of years ago, I'm not sure who here knows David Rowe. He developed Codec 2, the open source voice codec, and he also developed a number of open source modems. So David Rowe and I decided we're going to go make a telemetry mode designed specifically for balloon launches, more specifically for up and down balloon launches. So not your long duration floaters, that's covered by Whisper and other modes like that. This is a couple of hour up, burst, down kind of flight. We wanted fast update rates. We wanted it to be ultra reliable. We wanted it to be completely open source and be well performing. So what we ended up coming up with was a 100 baud FSK, 4 FSK modem with a bit of forward error correction added to it as well. Uses about 1 kilohertz of bandwidth. You can actually use less, but we're limited by the frequency resolution of our reference platform, the RS-41, which I'll talk about in a minute. And you can receive it with very, very minimal receivers. You don't need much to receive this telemetry. It's that robust. It's 100% open source from end to end. There are a number of different packet formats available, some of which you can go plug your own custom data in to send your own telemetry down. And it has become the standard tracking system for pretty much all flights in Australia and many, many flights in Europe, and also quite a few US launch groups. So it sounds like this. That was one packet. So performance-wise, it's decodable down to about -6 dB signal to noise ratio in a 2 kilohertz reference bandwidth. The next number is a little bit rubbery, but in terms of advantage over APRS, it's about 20 dB in performance advantage for the same transmit power. This is a combination of the difference in baud rate, for one, and also the removal of the double modulation, which you get in AFSK. In general, reception of this mode is only limited by radio horizon. If it's above your horizon, you'll be able to decode this with pretty much a quarter wave ground plane. As I said, very minimal receiver setups to receive this. So transmitters of this, the RS-41 is the reference platform, and Mike will talk a bit more about that later on as to how to reflash an RS-41. To get an idea of what you get out of an RS-41, you'll get about a day's worth of battery life transmitting continuously at 25 milliwatts. That's all we use. That's all we've ever needed. Works just fine. There are implementations available for other platforms as well. We're hoping the DFM-17 will become one of those eventually too. So we have a number of ways of decoding this. Horus GUI is probably the easiest place to get started. And I'm going to give you a brief demonstration of that. Again, the live demos. So this is SDR++. I'm just using an SDR as an example here. Using an RTL SDR, there's our signal in the center. And I'll bring up Horus GUI. And there we have it. So I'm actually using SDR++ to feed audio out via UDP, though a loopback sound card would work just fine as well. And we can see the telemetry being decoded here. No issues at all. And you can see the update rate every couple of seconds. You get a new position through. It's being uploaded to the web. So that's effectively it decoding. And if I do something a little bit silly here, and I'm going to try and intentionally lower the SNR, and it's too close. I can't do it very well. So anyway, can't get below about 8 dB SNR in this test setup. Anyway, it's very robust, can decode from a very, very long way away. And again, this software can also control rotators if you really need to point a rotator at your balloon. Where are we? There's also a command line decoder for a headless situation, for example, in the back of a car or on top of a mountain somewhere. Uses an RTL SDR as well. It can run on a Raspberry Pi or any other Linux computer, really. And it will decode or look in a given bandwidth find the signal, decode it, upload it to the web, upload it to HabHub and to SondeHub-Amateur, which I'll talk about in a second, and also can broadcast telemetry to the local network for local mapping in the terms of Chase Mapper, which again, I'll talk about a little bit later on. Again, all open source, available online. So an example of a minimal receive setup, I went out and bought a bunch of really cheap mag mounts from AliExpress. I think the cheapest was about $1 per unit. The one that's on the screen is about $3 per unit. Australian, this is, so half of that in US, I think. And that plus an RTL SDR, no preamplifier. The software I just showed you, no issues receiving a payload 125 miles away, or 200 kilometers away. And it's also worth noting that there's about a 6 dB SNR margin at this range. So I've got a 1 dB SNR, which I'm seeing on the packet. So theoretically, I should be able to decode no issues at twice this range. During our flights, we regularly see people receiving 500, 600 Ks away, even further, 800 Ks away in some cases if the balloon gets high enough. So no issues decoding at that kind of range. So telemetry needs to go somewhere. Many of you will be aware of HabHub. The problem we have at the moment is the HabHub servers the hosting arrangement has a time limit, and the Habitat database itself is becoming difficult to support in terms of software and dependencies. It was built in the early 2010s. And it basically hasn't been touched since then. So we needed something to replace it. So one option, which we're progressing with, is SondeHub-Amateur. So the SondeHub database handles 300 radiosondes a day or more. Making it support amateur balloon traffic was really a no-brainer. It can cope with that, no issues at all. So we've used what we've learned in SondeHub, and we have added support for amateur balloon launches, and we launched this late last year. We're taking data from a number of sources. We have an APRS-IS gateway, which is a lot faster than the HabHub one, I'll tell you that. That catches pretty much all APRS launches and also Whisper flights, which are feeding data into APRS. We also have an API, very similar to the SondeHub one, which is currently in use by the Horus GUI software and Horus dmodlib. There are a few Whisper launches directly feeding data into SondeHub-Amateur now. There'll be some LoRaWAN flights feeding data in soon. The LoRa system used in the UK and in Europe will be added, support will be added very soon as well. And there's also a library which can make uploading a lot easier. So SondeHub-Amateur looks very similar to SondeHub, funnily enough. It is based off the same code base, but you'll see there's a lot less balloons on it. So here we can see a couple of APRS floater balloons, well, probably coming in via Whisper more than likely. And in here is a balloon currently in progress from PE2BZ, Ben, which has been really nice because I was going to have to launch a balloon myself to give an example. You can see that balloon, off it goes. Now, the other advantages that this site has over HabHub, so we still get our live balloon flight predictions. However, what we can do on this site is we can actually customize the prediction settings for your own flight. So if your flight isn't going to do the standard 30-kilometer burst and 5 meter a second descent, you can come into here, you can put your call sign and your information in, and it will use the right prediction settings from that point onwards. Anyone can go in and update those settings. So in this case, I've configured this flight to have a floating prediction profile because it is in fact floating. Other flights that are currently in progress. We've got this one here from Poland, and there's a few others as well, test launches as well. And there's W5KUB's flight too, which is pretty cool. Now, something we've added, so many of you may be familiar with the high split predictions on HabHub. On this site, we have what we call our float predictions. And this may make a liar out of me, but we'll see whether this works. There we go. It looks very similar to high split, but it is not high split. This is using the GFS model, and then it's using some different initial conditions, different altitudes in particular, and plotting them on the map. This is run on demand, so there's no need to ask for it to be set up. You just go to the site and click the float button, and you have your long duration float predictions out to, I think it's a couple of days, plus 84 hours, so 3 and a bit days for each of these different altitudes. So that's a new feature. It's been in there for a while, but it hasn't been that well publicized. So that's the SondeHub-Amateur tracker. Something we've added in about the last 2 weeks is dashboards. So HabHub had the concept of flight documents. We're not going with that on this system. Instead, we have a Grafana instance. So Grafana is a graphing system. It peers into our database and allows you to extract and plot data. This is what we call our flight view. And what this shows is when a particular call sign has been heard, in this case over the last week, but I can expand that to even further, but I'll use 7 days for now. And we can choose a flight and plot it. So as an example, I'm going to pick on one that was shown, was on the list recently. Where is he? W9YJ13. So I've chosen that flight. Now I have to go and adjust the time frame, I believe. I think I've chosen a bad time frame, but let me just adjust that. No, maybe not. Actually, I'll pick on Phil. Probably a better one. Here we go. So here's a flight from San Diego, and we've chosen a given time range. I can go and just select the time range of just the flight. There we go. And we get plots. Everyone loves plots, right? So we have ascent rate, both ascent rate as reported but in the Radiosonde telemetry in this case, and also calculated payload data, payload sensor data, I should say. So we've got pressure, temperature, humidity in this case. And here's something which is a little bit different. So the Horus decoders, the Horus binary decoders will report all sorts of metadata as it uploads telemetry, including signal to noise ratio and the reported frequency. So you can see the signal to noise ratio of the different receivers throughout the flight. So here's the receive site on the hill, W6 Sun Toro. Here's Phil's home station, pretty good SNR until descent, it seems. You can also see how the frequency of the transmitters have drifted throughout the flight, and it's done some wobblies on descent, presumably due to the going through, descending quickly. That's kind of something a little bit different. And also we have a pie chart. Here in Adelaide, our launches are social events. We get the word out ahead of time, and we end up with many, many people receiving. Like last flight, we had 40 receivers going just because they could. And they get their name on the pie chart. So there's competition who can get the most packets through. There have been warnings of pins in coaxes to get higher up on the pie chart. But yeah, so things that we've put in place to kind of get the community more involved in our flights, and these dashboards help with that. Other thing you can do here is you can export the flight area of the flight that you're seeing. So we've chosen this time range. We can download the data as CSV, a KML file, or as JSON. So you can get access to all of your flight data in various ways. So this is very, very new. It's only got implemented probably about 2 weeks ago, and we're interested to see how this is used. This can be run live, by the way. You can adjust this to update regularly and show the last few hours. So this would be great for classroom displays, I think. All right. Where are we? So what if you don't have access to the internet? Many of our early launches, it's just as bad here in Australia as it is in the US. We go out of phone coverage pretty quickly when we leave Adelaide. So early on, we started developing offline mapping systems. We started out with a mapping system based off of a Windows-only software called Aussie Explorer. That worked pretty well for us for a few years, and then it became too hard to support. So I wrote Chase Mapper. This is a browser-based mapping system. It runs on a Raspberry Pi or any other Linux machine, really. In my case, it's a Raspberry Pi bolted into the back of my car, the same one that's running Auto-RX and other decoders. It ingests telemetry from multiple sources, and I think Mike's going to talk about some of the things that he's been doing with it. It'll do online flight predictions, live predictions. It'll do offline flight predictions with downloaded wind data. It'll use online maps. It'll use offline cached maps. It'll report your location to the various online mapping systems, so people watching from home can see where you are. And it can also plot bearings for ARDF hunts as well, which is something that's been kind of fun. So live demo again. Here it is. And unfortunately, this is a pretty boring demo because there isn't actually a flight in the air that I'm tracking. But this is one that I've got running on the bench, the one that I was just decoding earlier. And again, I've got no GPS attached right now, so my car isn't showing up. But we can see the balloon on the ground. In this case, we can see predictions showing up. In this case, it thinks that it's ascending very, very slowly because it's just sitting on the ground. It will also provide a abort prediction. So a prediction of what happens if you cut the balloon away or terminate the flight now. Very handy if you have a cut down on your flight and you want to decide when to trigger it. So you can also upload our position to the Hub and or SondeHub maps as well, if we choose to. So yeah, Mike will give a bit more of a talk about that and how he uses it. This is what I run for all of my chases. And essentially, this is how we end up at the landing spot before the balloon gets there and watch it land on almost every single one of our flights. Without this, we wouldn't be able to do that. I talked about bearings before, just very quickly. About a year ago, I added support for plotting bearings from a Kerberos SDR and more recently a Kraken SDR DOA system. This is not balloon related, but it is kind of fun regardless. So here's an example showing a whole bunch of DOA, so direction of arrival bearings, plotted on a map showing you can pretty clearly see where the transmitter is in this area here. So just a bit of extra fun that I can do with Chase Mapper. So last but not least, there's the imagery system that we've been using for the last few years as well. So about a year after we started doing Horus binary, David Rowe and I looked at each other and kind of went, we have a lot of excess SNR on this system, about 30 dB of it. What happens if we try and translate the excess SNR to high data rates? So we decided to make this system and push things to the limit. So imagery downlinks from balloons have been done for a very long time. SSDV, or slow scan digital video, is a protocol developed in 2010 and has been used in the UK and many other places since then. It's JPEG broken up into a protocol which allows images to be reassembled from multiple receivers without the complete image. So if you just get a part of an image, you can still get a workable image out of it. Been around for a very, very long time now. So we decided, and normally they've been using it at very low data rates, so like 300 baud. We thought we can do better than that. And we decided to push it as high as we could, almost. Ended up settling on 115 kilobits per second, which happens to be the same bit rate as a serial port for various reasons. We added some forward error correction in the form of low density parity check forward error correction. And we run this on the 70 centimeter band. I must admit, we're lucky here in Australia in that our bands are pretty quiet, so we can get away with a lot of things, such as this. We run 50 milliwatts on 443 megahertz. For you, I think you'd be wanting to run in your ATV segment more than likely. This is our ATV segment, 443 megahertz. We only run 50 milliwatts. The transmitter is a Raspberry Pi with a Raspberry Pi camera and in this case, it's actually a LoRa module, but we're running it in FSK mode to produce frequency shift keying. Runs off 3 AA batteries, total weight 150 grams. And it will run for about 7 or 8 hours, which is more than enough for a regular flight. We built a custom modem based around David Rowe's codec 2 and FSK modem work, which performs to theory. It works very well. The minimum detectable signal is about negative 115 dBm, thereabouts. And we can downlink a 1080p size picture in about 30 seconds, which is very, very cool. And we use spatial diversity. So multiple receivers receive telemetry. Each packet is uploaded to ssdv.hubhub.org, which reassembles the images in real time. So if we get more than 2 or 3 receivers, we will have rock solid images throughout the entire flight, which is just incredible. So it's very, very cool to watch these flights in progress. Again, open source. This protocol has been around for a very long time. So some example photographs. Yes, these are actually off the radio link. I'm not kidding. From one flight back in 2017. And then from our last flight where we got to 40 kilometers, 40.1 Ks, 131,000 feet, which was our record. That one's a little bit blurry because the camera lens had a problem. But yeah, this is the kind of imagery that we're downlinking essentially live from our flights nowadays. Receive stations for this. So software-defined radio-based, Linux only, unfortunately. I might get around to making a Windows version at some point, but that's a fair way away. So Linux-based is a web interface. I'll show you in a second. You do need a little bit of gain. 5-element Yagi is usually enough, or almost always enough with a preamplifier. On my chase car, I just run a turnstile with a preamplifier. That gives me perfect coverage during the chase. And we have seen 200 miles of rock solid decoding range with a 9-element Yagi antenna and a preamplifier. So that's pretty cool. It's a very, very long range for that kind of data rate. To see it in real time, I have a Wenet payload sitting behind me somewhere, and it's currently taking a photograph. If we just give it a second, it will start transmitting and you'll see it actually downlinking the image to the receiver in real time. Here we go. That's the kind of update rate that we're seeing. So that's it. That's what we see in real time during the flight. So that's a 1488 by 1120 pixel image being downlinked. And we get this, so yeah, over, as I said before, over about 200 miles of range, which is pretty cool. So,
Mark, remind me the bandwidth that's using.
Thanks for that, Mike. About 300 kilohertz. That's not so good. I appreciate that. But if you can find an ATV segment, I'm sure you'll find somewhere to fit it. That's because the transmitter we're using isn't particularly well filtered, and we are running at 115 kilobits per second. But it's not too bad in the grand scheme of things. For what you get out of it, it's pretty cool. Anyway, I'll wrap it up there. There's a lot of links all on GitHub, mostly on github.com/Project Horus. Everything we do is open source. We invite contributions, we invite suggestions, and we look forward to seeing what it gets used for. So I'll leave it there. I've got about 5 minutes for questions, I believe.
Everyone's speechless.
There's actually a bunch of questions in the chat I can see.
This is Tony McMonagle. I have one quick question. I think the amateur Sonde site is fantastic. I was noticing when I went to it that I saw, like, for instance, the W5KUB balloon. But if I had a balloon, I have a balloon up now. Is there something special that has to be done to get a balloon added?
If it's on APRS and it's a position report, it should end up there automatically. If it's an object, it probably won't show up, unfortunately. The reason behind that is because all the Radiosonde traffic ends up as objects. So how is your balloon transmitting?
It's APRS, and it's it's being transmitted to APRS, it's showing up as a balloon, as a -0 ID.
-0. Interesting.
I think
what call
that's
sign?
the one. It hasn't been up for about 15 hours because it's over Russia.
Oh,
But it was
okay.
Yeah, that might. And I think AB5SS has one as well. Not sure if John's still on. Yeah, John, you have one as well, right?
No, that one's whispered, not APRS though.
Oh, okay.
Yeah, it's whispered.
Though if the whisper traffic ends up on APRS IS due to an importer, it'll end up on the SondeHub-Amateur map as well. So I see WA3 USG is over the Baltic Sea.
It was over the sea near Turkey.
Yeah. Yeah, I can't see your particular flight. There's a number of checks that are made to try and avoid importing Radiosonde traffic, of which there is a lot on APRS IS. It's possible you may have tripped one of those. But yeah, if you let me know the call sign, we can go and figure out why it's not going in.
Sounds good. Yeah, really nice work.
What is the address for the amateur tracker on SondeHub? Is it tracker.sondehub.amateur.org or what?
Amateur.sondehub.org.
Okay, amateur.sondehub.org. Okay, thanks.
Or ham.sondehub.org will also work, if you're that way inclined.
Question mark. I've noticed on HabHub that the APRS importer drops out for long periods of time, so there's gaps in data. Is that a database problem, or
that's an importer problem? The importer isn't keeping up, and effectively it got to the point that it just. So to be brutally honest, HabHub probably isn't going to get much more support from now on. So don't expect to see much getting fixed on HabHub. It'll be most stuff. Well, at least we are supporting SondeHub-Amateur nowadays. So, yeah.
Oh, and I do see the AB5SS that's showing up.
Okay, cool. Yeah, it may be that it's an older, like it was a few hours ago. But by default, we only show 12 hours of backlog. But you can change that one day.
That's probably what it was. It's over more than 12 hours.
Yeah. So top left-hand corner of the map, look for a drop-down box, and you can change the history on there.
Great.
Yeah, my experience with amateur.sondehub is that the performance is just superior to habhub.org. When doing a live balloon chase and trying to rely on the predictions to see where it's going, I don't even use HabHub anymore. I use amateur.sondehub, and it works so much better. So I definitely suggest folks doing chases to use amateur.sondehub now.
Yeah, and you get predictions, unlike APRS.fi. We are considering adding in support to import chase cars from APRS, but that is a bit more effort involved and a bit more care required as well, because we don't want to end up with chase cars all over the map from random, APRS traffic. So it is also very surprising how many cars are running around with balloon icons, which has made our life very difficult. Because, we're filtering based upon balloon icons because we're assuming balloon icons are balloons. Most of them are, not necessarily high altitude balloons. So it's also worth noting that on SondeHub.Amateur, actually, I will show you this. By default, APRS data is only shown on the map if it has been above 2 kilometers. What's that in feet? I'm not sure, sorry. At some point during its flight. However, you can show low altitude APRS in the settings pane, and you will suddenly see a whole lot more traffic on the map, which is all the people testing trackers on the ground, or it could be, this is probably an example of someone with a car, -9, yep, mobile, using a balloon icon. So thanks for that, Keith. There's a reason why these are filtered out by default. But yeah, you can see your testing traffic. And then once your balloon is in the air, it'll just automatically start showing up.